When I first introduced chemical equations to you guys, I kind of went backwards. Get your stuff out, guys. Soham needs a writing utensil. Soham, where's your writing utensil?
Oh, I have it, right? But it's too thick. It doesn't look nice, right? It doesn't look cute.
So get a writing utensil that you're happy with how it looks. Okay. So I want all y'all to find me the pages of word equations up at the top. I'm going to flip back for a second. So, back when I first introduced chemical equations, don't go to this page, go to the page that says word equations. Back when I first introduced these things, I said there are a bunch of ways that you're going to be given these things. A chemical equation is a statement that uses words or symbols. And then the first kind of equation I said was, well, you could be given this as a word equation. And then I kind of just glossed over that fact. What we're going to do today is we're going to go back to that idea of you can be given this thing as a word equation. And then what do you do with it is going to be the question. Which is why when I handed back your guys' chemical naming and formula writing quiz in Paris, I made you guys do corrections on it because that's what we're going to look at doing today. So, sometimes you're going to be given a chemical reaction, and it's not going to be given to you as a skeleton equation that I then ask you to balance. It's going to be given to you as a word equation. I'll just share the names with you, and I'll be like, okay, so this is going to react with this, it's going to produce this, and I'm going to use the names. For example, hydrogen is going to react with oxygen, it's going to produce water, down here at the bottom. And then that should mean something to you so that in your brain you're looking at, okay, well, he says hydrogen and oxygen gives us water. This is true. And so what does it mean for hydrogen and oxygen to give us water? Well, hydrogen is going to show up in a particular form. Oxygen is going to show up in a particular form. I know the formula for oxygen is H2O. Okay, well, today we're going to look at how to go from one to the next. And just to show you where we're going, in the lab, I'm not necessarily going to give you a skeleton equation or even a word equation. I'm going to say, in this lab, you're going to take this object and you're going to take this object. You're going to react them together. It's going to produce this. For example, this guy here, which is an example we'll look at maybe today, maybe tomorrow. A piece of metallic zinc, that should say placed, not pulsed, is placed in a blue solution of copper 2 sulfate. A reddish-brown layer of metallic copper forms in a clear solution of zinc sulfate. That is a picture of what's actually going on in the lab. From here, you need to turn that into a word equation, to turn that into a skeleton equation, to turn that into a balanced, full-blown chemical equation. And so that is as close to real life as we're going to get until we actually step in the lab and then do these things. So today we're going to go back. We're in baby steps. We started with skeleton. I taught you how to balance. Now we're going to take it back a step and say, okay, well, what if I give it to you as a word equation? What are you going to do then? So here we go. Sometimes you are given word equations and asked to create balanced equations. And now there's another set of details. We're constantly building on the details. This will not be a review of anything you did in grade 9. This is new. So, the first thing you need to do when you're given something like this is to turn each compound, if I give you the name of a compound, or element name, if I give you the name of a singular element, and you need to turn that into the chemical formula. You will need to be very careful with this step. You will need to recognize certain things. You're going to need to go back and say, okay, well, when I provide to you the name of the compound, is that thing ionic? Is that thing covalent? Depending on if it's ionic or covalent, you're going to build the formula a particular way. If it's covalent, we're just going to use the prefixes that are given. If the thing's ionic, Well, now we've got all of the ionic naming rules that I gave you before. Is there a polyatomic? Is it multivalent? What charge are we using? Well, the Roman numerals will tell you that if I give you a Roman numeral. Is the thing a simple ionic? And the absolute worst case scenario that I could give you in a situation like this is I don't give you a name that's obviously ionic or obviously covalent. What if I give you a common name? What if I tell you you're reacting with bleach? Well, that B-L-E-A-C-H, 6-letter word, bleach, gives you zero indication what the chemical formula is. If you don't know what the chemical formula is, or salt, I say salt. When I say salt, what do you picture? Well, I didn't say table salt. The next chunk we're going to look at is we're going to look at a section on acids, bases, and salts. And I'm going to teach you that any product you make when you react an acid and a base together is a type of salt. So if I say salt, you think table salt, but not all salts are table salt. And so if I give you the common name for these things, now you need to actually start to ask yourself questions like, what does he mean? Like, what is the context of the problem? Does it make sense to assume that when I say salt, you think table salt? And then what is the chemical formula for table salt? Yes. I would love nothing more than to do that for you. Is that enough? That says ionic. That's probably the one you're struggling to see, yeah? Simple ionic, I-O-N-I-C. I ran it to the edge of the page. So it's something you've done already. We've looked at this. This one was a struggle for a bunch of you, and that's why I asked you to go back and review and correct your quiz. This is what's going to be hard. Once you've got this step done properly, this is where you're going to then start to set up your skeleton equation, and then you're going to be able to go ahead and balance the thing. So now is a good time to introduce to you guys. You may have seen it before. When we were doing this with Lewis diagrams, I introduced this idea to you. But there are elements that when we just use their name, if I tell you that you're working with oxygen, you don't just have O. Because what does oxygen do when oxygen is by itself? If I just have a bunch of oxygen sitting around, if you think back to the Lewis diagrams, what does oxygen want to do? It wants to take electrons. So if you have two things that both want to be in possession of the same thing, my 2-year-old and my 4-year-old want the same stuff. So they have to share. So the oxygens are going to get close enough. If all you have is pure oxygen and they're just hanging out by themselves, it's going to get close enough so that the oxygen is going to share. We don't call this anything other than oxygen because that's what it is. But what's the chemical formula for this? How many oxygens are present? There's 2 of them. So when oxygen is by itself, oxygen is known to be O2. And oxygen is one of a group of elements that are what we call diatomic. This word diatomic, di is the prefix we've used before. Di means 2. So a diatomic element means when I give you the name for that element, there are 2 atoms of that element that show up. So we've got some diatomics. Here are the diatomics. So if you notice in the chemical equation on several of the previous pages and in the Lewis diagrams was a really good example of us doing it. Oxygen on its own shows up as O2. It's because oxygen naturally exists, and we can see from the Lewis diagrams that I had you draw before, oxygen naturally exists only as a diatomic element. And it's not the only one. Oxygen does this. I've given you a section of the periodic table. Oxygen does this. Nitrogen does this. Fluorine, chlorine, bromine, iodine do this. Hydrogen does this. These are the diatomics. But I've also told you that there's on the side here, the title, diatomic and polyatomic elements. Sulfur and phosphorus, these guys here, exist as polyatomic elements. Sulfur on its own, if you have a lump of sulfur, you go to Vancouver, you go to Stanley Park, you look across the harbor to those big piles of yellow, that is pure sulfur. The chemical formula of that, S8. Sulfur on its own exists as 8 atoms of sulfur, all Lewis diagram bonded together. And phosphorus shows up as P4 often on its own. I'm ready, okay. Just tired. Your sister said you guys landed at like 1 a.m., 12:30, something ridiculous like that? Yeah. Do what you got to do, as long as you're okay. Okay, so we got the diatomics, these brown ones here, the polyatomics, these 2 green ones here, and a way, this is not necessarily going to work for everyone, but a way to remember the diatomics is to visualize them on the periodic table, forming the number 7. There's this guy here. And there are 7 of them. 1, 2, 3, 4, 5, 6. 7 is hydrogen. Someone also once told me that they actually represent a hockey stick and puck, which is just so Canadian of them. Because you've got the hockey stick, and then you've got your lone hydrogen puck. I don't know. It's a way to memorize it. But what you need to now start doing is when I give you the name for these things, you need to be able to remember that on their own, this is what they'll do. And so when they show up as a single element named that way, this is what you have to do. So I'll do a couple examples, then I'll free you to play with this. Here we go. So if I tell you hydrogen and oxygen react to form water, what you will need to do immediately is say, okay, well, hydrogen is one of these diatomics. It's that guy right there. So when I say hydrogen, that on its own is actually just H2. I'm getting a phone call from Jamaica. That's fun. So hydrogen is H2, oxygen is O2. Oxygen is one of these diatomics, and they're going to produce water. Well, that's one of those common names. I expect you all to know what water is. You've been familiar with water your whole life. Water is H2O. And then you need to make sure that when you're building your skeleton equation, you leave space for the balancing of this skeleton equation. And now we're actually going to take the time to go ahead and balance this thing. We draw the line. Well, what am I counting? I'm counting H's and O's. H's and O's. What's the first step here for balancing? Counting each side, 2, 2, 2, 1. H's are balanced, so we're going to look at the oxygens. Elijah, put your phone away. What am I doing here to balance these things? I'm going to balance well, H's are balanced. 2 of each. So let's balance the O's. What am I going to have to do? By what? So Hum says put a 2 there. Whoa, no. Simple. Keep it as simple as humanly possible. I have 2 oxygens here. I have 1 oxygen here. This guy's showing up in groups of 1. So I put a 2 here. This is good to review. Good thing you're not writing the quiz today. Put the 2 out front here. Now I recount everything. 2 groups of water. 2 times 2 is how many hydrogens? How many oxygens do I have now? So now my oxygens are balanced. We have to go back and fix our hydrogens. What do I have to do? Toss a 2 here. That's going to give me 4. Now we're balanced. No 6s, no 3s, no craziness. Just 2. And then if there's a gap, we can toss a 1 in there. So what this is going to tell you is that you need twice as much hydrogen as you have oxygen. So you would need 2 liters of hydrogen gas to react with 1 liter of oxygen gas, and it's going to make 2 liters of water, is what this means. So we went from the word equation, we built each formula based on our naming rules and this new rule of diatomics that I'm exposing to you to. We created the skeleton equation, we balanced the thing. We okay? Air is complicated. Because when you say air, you don't mean what you should mean lots of the time. Because air is made up of hydrogen gas, well, it's made up of nitrogen gas, made of oxygen gas, made of carbon dioxide, and whatever other gases are present. Okay, flip the page. I'll do a couple examples off of here, and then I'm going to get you guys to practice this. So, let's take a look at question 3. We're going to do 3 as an example. So here's the word equation. Sodium plus water. This is a reaction you should have seen in grade 9. Not every teacher does this. Mine would have seen it with either Mr. Gebrand or myself. I know Mr. O has our lab tech do this, Christy do this. Easton does this. Miss Gill is often too scared to do this, is what she has told me. Not to throw Miss Gill under the bus. She's a lovely science teacher, but she is too scared to play with chemicals, and that's okay. So this is a reaction we've seen. You toss sodium in water, what does it do? Boom. Blows up, sparks everywhere, it's awesome. Why? Well, here's the reaction that's happening here. When you react sodium with water, you produce sodium hydroxide and you produce hydrogen gas. It's not the sodium that's burning, it's the wildly flammable hydrogen gas that's being produced that is flammable. So let's write this out. On its own, sodium is what? Is sodium one of the diatomics? No, it's not a diatomic. It's just an element. So what is the formula for sodium? It's just Na. It's not diatomic. It's just an element. There's no compound there. You use the symbol for the name as written. We got Na. Leave the space. Plus, water you're all familiar with is going to be H2O. At this stage, I will tell you what it produces. At the end of this chapter, I'm not going to give you this right-hand side. You got to figure out this right-hand side. It's fun. But right now, I'm going to tell you, sodium plus water is going to react. It's going to produce sodium hydroxide. Well, okay, what is sodium hydroxide? That is a compound made up of sodium, which we know to be Na. Charge on sodium is +1. What is hydroxide? It's OH. It's a polyatomic ion. What's the charge on hydroxide? -1. So this is an ionic compound made up of sodium metal and a polyatomic ion hydroxide. So how do I make the formula for sodium hydroxide? Well, we had 2 ways to do it. I gave you a long version. So, okay, well, if this is +1, this is -1, how many do I each need to balance out? Or we swap, drop, reduce. So this lends itself to swap, drop, and reduce. This is a nice, easy one. I just need one of each. So this thing's going to become sodium hydroxide is NaOH. I leave the gap out front. Plus hydrogen. Now, you need to remember, hydrogen is one of these polyatomics. On your, one easy way to remember this is that most of the things that show up diatomic are actually colored in on this table. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine. Iodine's not, but it's one easy thing to remember. This is the table I'm going to give you, and lots of the things that are diatomic are colored in. So these guys. So hydrogen is one of those. So this you need to recognize as being H2. And then this is the thing that you would then go ahead and balance. Comments, questions, concerns about what I've just done? Shall I do another? I feel like I probably should. I'll do 2 more. I'll do 5 and we're going to do 7. I'm not going to balance my examples. I'm not balancing. I'm just building the skeleton equation. I will leave you to go back and balance. Let's take a look at 5. Okay, so the word equation says potassium iodide plus chlorine reacts to produce potassium chloride and iodine. Okay, well, let's build all of these pieces. Potassium iodide, there's no symbol in there, so this represents the name of a compound. Let's build the compound. To build it, I need to start writing down the various pieces. Potassium is K. Charge on potassium is +1. Iodine is I. Oops, I is over here. That's a mistake. It's got to charge a -1. So the formula for potassium iodide is going to be what? It's going to be Ki. Come on, you silly thing. There we go. Okay, so this guy's just going to be Ki. Leave a blank out front. Plus, oops, so I have to rewrite the word in here. CHLORI. Chlorine, what's the formula for chlorine? It is not Cl. Chlorine is one of the 7 diatomics. So it's going to be Cl2. The symbol is Cl, but chlorine, again, is one of these ones that you need to go back and look. Oh, look. This column is part of this column are going to be the diatomics. Chlorine is that guy right there. Chlorine on its own is Cl2 every time. Okay, now let's make the products. Potassium chloride, that's a compound made up of K, charge of +1, and chlorine, charge of -1. So what is the formula going to be for potassium chloride? Why? Your swap drop. Charge, if the 1, there's nothing to reduce. So potassium chloride is just going to be KCl. Plus what? What is iodine? I2. Iodine is one of those diatomics. And now you could go ahead and balance this thing. I'm not going to. I'll leave you to balance. I'll do one more example for you, and then I will let you work on your own. Here we go. Number 7. Magnesium plus copper 2 sulfate reacts to produce magnesium sulfate and copper. So, magnesium. Magnesium's there all on its own, separated with a plus sign, so it's just magnesium. What is the chemical formula for just magnesium? It is just going to be Mg. Magnesium is an element. Magnesium is not diatomic or polyatomic. It's just Mg. Cool. So with the Mg, we're going to react it with what? Copper 2 sulfate. Now, there's a Roman numeral in this one. What does that Roman numeral tell you? The charge on what? The copper. So copper is Cu. That Roman numeral tells you the charge is +2. And we've got sulfate here. Sulfate's a polyatomic ion. It ends in ATE. So you're going to go back and you're going to look at your polyatomic ion chart. Sulfate is what? What's the formula for sulfate? No, that's hydrogen sulfate. It's just SO4. And the charge on sulfate is, in fact, -2. So if I have Cu with a charge of +2 and SO4 with a charge of -2, when I bring those together, what's the chemical formula going to be? It's just going to be CuSO4. Because this one's got a charge of +2, this one's got a charge of -2. So if I swap and drop and then reduce, it's going to go 2 and 2. But 2 and 2 are divisible by 2, so I just need one of each. No brackets because I only need one of the SO4 to balance out the charge on my copper. So then, and again, feel free to stop me if you've got questions or if I'm going too fast. Be brave. We've got magnesium sulfate. Well, magnesium is Mg. What's the charge on magnesium? Because I'm going to have to combine it with the sulfates. Double check your periodic table. +2. Sulfate, polyatomic ion, SO4, charge of -2. So what's the formula for magnesium sulfate? It is, in fact, going to be just MgSO4. Plus, leave a space for copper. Yes, it is not one of the diatomics. None of the metals are diatomic. So this guy's just going to be Cu. So now we've created the skeleton equation that you can then go ahead and balance. This guy here? Because it's not diatomic. Mg metals just show up as themselves. Magnesium just shows up as a bunch of Mg's hanging out together. The charge only matters when you build compounds with it. You haven't built a compound out of the magnesium yet. It's just hanging out there. When you combine it with the sulfate, then we care about the charge. Because at that point, it's going to give up electrons to ionize. It doesn't give up electrons until it's with something that wants it. Does that make sense? I'll take kind of. Imparis. Doesn't matter. Doesn't have a charge. It's an atom. You've got a bunch of copper atoms that are produced. Chargeless copper atoms. Okay, and so a way to remember this, is anything that would make a positive charge only gives up electrons if there's something there to take the electrons. Like here, magnesium, when we have magnesium sulfate, the reason we have magnesium sulfate is because magnesium on its own is happy to give up electrons, but it's not going to unless there's something there to take it. So in the presence of sulfate, sulfate says, yeah, I'll take those. Come on over here. Give me what you have. And then we care about magnesium now has a charge of +2. Sulfate's got the charge of -2 because it took the electrons. And the copper that was bonded to the sulfate with a charge of +2 gets its electrons back. Because the sulfate's now like, you know what? No, I don't want your electrons anymore. You can have yours back. I'm going to take magnesium's electrons. And so then copper's hanging out over here as an atom now, no charge. Why this exchange happens is more complicated than we're going to get into in this course. But that exchange is what's happening. Yes, Imparis. Yeah. No, it gave up 2 electrons to attract the sulfate. But in the presence of magnesium, like you can think of this as like a super toxic relationship. Copper and sulfate are in a relationship together. It's the meme. It's the meme. It's the meme where okay, you know the meme? You know the meme I'm talking about? Okay, I'm gonna act out the meme. I need 3 of you. I don't care which 3. Stand up right now. 3 people. On your market, say go. Harbir, Kim, yeah, Luca, and Olive. You're volunteering. This is actually great. It's the opposite of the meme. I love the meme. Okay, cool. So, Harbir, stand over here. Olive, come stand over here. Luca, I want you to stand here, look that way. You, okay, you stand over here. And you're walking this way. Olive, you're walking this way. And so here's what we have. We have magnesium. We have copper. And we have sulfate. And as the magnesium and the copper to sulfate get, yes, it's this meme. You turn and you look up, you turn and you look. You're like, ooh, magnesium. It's that meme. This is what's going on. Thank you for demonstrating. You see the meme? Yes? You've not seen the meme? Oh, it's usually it's a guy with a girl and another girl walking by. This is a role reversal. Olive's checking out the magnesium that's walking by. Magnesium. I pointed out that magnesium. You can just keep walking. It was a role reversal of the meme. But it's the meme you've seen. It's an old one. But that's what's going on here. You have copper to sulfate. It's already a compound together. In the presence of magnesium, sulfate says, I see something better. Excuse me, copper. You can have whatever I've given you back. And I'm going to go hook up over here. That's what's happening. That's functionally what's happening here. Obviously, it's fundamentally different because there's no emotions involved in this. It's not now like magnesium and copper are super crushed by this. But that meme is what's happening here. Now, the why, so the Himparus asks kind of the why. Why? The why is really complicated. Because sulfate got what it wanted from the copper. Why would it then just jump to magnesium? The why is complicated, but it does. That is what will happen. So there is, how much time is left in class? I am not going to do the word equation part of this. Class ends at 1:15. Cool, you got 20 minutes. Here's what I'm going to get you to do. With the time that remains. Yes, it's that meme right there. Thank you. It's this meme right here. The distracted boyfriend meme. Except it wasn't the distracted boyfriend. This was played by the role of Olive. Or Olive played this role here. And these two, this was Luca, and this one was Harbir. Harbir is about to get ditched by Olive for magnesium. Thank you. Distracted boyfriend meme, that's what it's called. Okay, so what I'm going to get you to do, with the time that remains, I am not going to make you go back and do all the balancing. I just want you to go through the actions of putting the equations together. I'm going to give you a quiz next week, and you are going to have to go through the active balancing at that stage, but you don't have to now. I just want you practicing putting it together. So I want you to do questions 2, 4, 6, and then 8 through 12. So not 1, 2, 4, and 6. And then, because I forgot to put this in your, oh, wait a second. Nope. Maybe I should save this. No, I'm going to give this to you now as well. In addition to those, what is that? 1, 2, 3, 4, 5, 6, 7, 8 questions. I want you to come get this paper as well. You betcha. And I want you to do that page for homework as well. You do not have to balance. I just want you to build at this stage. Okay? On your mark, it's a giver.